All right, here we are for part 3. This is actually going to be 4 parts altogether. I changed my mind as I was working through this. So for this one, we are not going to look at roots yet. So I'm going to cross that out. We're just going to look at powers of complex numbers. So before we do that, I actually want to talk about a different notation. It's called Sis Notation. It'll make sense why it's called Sis Notation. But anyway, we're going to look at that first. Then we're going to look at powers. So this video is going to be pretty straightforward. So first of all, the Sis Notation. So you probably have been noticing, if you've been working through the homework, excuse me, for each video before watching the next video, you probably noticed, it's a kind of a pain to write. I mean, standard form, we have A plus BI. Nice and short, simple, sweet, time effective. But then we have trig form, which is R cosine theta plus I sine theta. And although some operations with it are nice and quick, writing it every time is kind of a pain. But there's a quicker way to write it. Not everybody uses it, but it is a standard notation that is accepted. So we keep writing the same format every time. There's always an R, there's always a cosine, there's always an I, there's always a sine, and there's always a theta. And that theta for the cosine and the sine are always the same. So why write it every single time I write all this out? So instead, it's R sis theta. And it has all those parts. So there's the R right there, the C for cosine in sis, the I in sis, the sine, S, and then we have a theta. So R sis theta means the same exact thing as R cosine theta plus I sine theta. Just a different way to write it. It's a little faster. So a quick example, if I had 3 cosine 45 degrees plus I sine 45 degrees, rather than writing that out every single time, you could just say 3 sis 45 degrees. Same exact thing. If we had 2 sis 5 pi over 7, that is the same thing as 2 cosine 5 pi over 7 plus I sine 5 pi over 7. Means the exact same thing. So I'm going to be using that notation a lot throughout the next 2 videos because it's just easier. All right, so goal number 1, check. Let's look at finding powers now. And powers are pretty straightforward as well. So I'm going to scroll this up. Powers of a complex number in trig form. It actually comes from the fact that we know how to multiply efficiently. So if I let, well, let's just do an example together, and then I think we'll do a few examples. I think you'll see the pattern. If I take R cosine theta plus I sine theta, and I raise that to the second power, first of all, it's kind of a pain. Why don't we just go ahead and use that notation, sis notation, because remember, same thing. But if you recall from multiplying, what do we actually do for multiplying? Well, actually, let me first write this as multiplication. So this is R sis theta times R sis theta. We've turned it into a multiplication problem so we can use our rule. And remember, the rule was multiply the radii, R times R, and add the angles, add the arguments, theta plus theta. But we can write that as just R squared sis 2 theta, which, changing it back, just so we're clear on the notation, remember this is the same exact thing as R squared cosine 2 theta plus I sine 2 theta. I think we might see a pattern already, even though we've only done one problem. Let's just do one more, and then I think we can generalize. So I am going to just use the sis notation now. So I'm basically going to start with this form right here to a power and end with this form right here. So if I have r cis theta to the third power, well, we know that that is r cis theta times r cis theta times r cis theta. And again, from multiplying, we know that we just multiply all the radii and we add all the arguments. Okay, so when you have 3 r's, that's r cubed when you're multiplying them, and then theta plus theta is going to be 3 theta. So now let's see if we can generalize. If you have r cis theta to the nth power, pause the video if you want, think about what that would be. And if you were thinking r to the nth, cis n theta, then you were right. And you can see that it works out. When we were raising it to the second power, you're going to have 2 r's that you multiply, so it's just r squared. When you're raising a complex number to the third power, you're going to have 3 r's that you multiply, so it's r cubed. This time you're raising it to the nth power, so you're going to have n r's that you're multiplying, or r to the nth. And then same thing for the thetas. When it's raised to the second power, you're adding 2 thetas, or just 2 theta. When you're raising it to the third power, you're going to add theta 3 times, which is 3 theta. So when you raise it to the nth power, you're going to add theta n times, so it's just n theta, and that brings us to Marvis Theorem, which is simply this. And I'm not sure why it gets its own name when this one's so straightforward, and yet the roots that we're going to do in the next video is much more complicated. Sorry, my grandfather clock. Alright, so if we let z equal, now this time I'm going to use the longer notation, make it a little more formal, equal cosine theta plus I sine theta, then z to the nth will equal r to the nth cis, whoops, I'm going to use the other notation, cosine n theta plus I sine n theta. And there it is. So now let's just do a couple examples. You don't want to do videos, you're probably sick and tired of watching them. But anyway, let's do a couple examples and then we'll be done. Very quick examples. So if we do 3 cis 20 degrees to the 5th power, think about what that would be. Pause the video again if you want. And it's just going to be 3 to the 5th cis 5 times 20 degrees, which will be 243 cis 100 degrees. And you can leave your answer like that. That is an accepted form, like I said. But just to reinforce it, remember that is the same thing as 243 cosine 100 degrees plus I sine 100 degrees. How nice is that? Yay! All right, let's just do one more example, and yeah, then we'll be done. So what if we had, let's do 2 minus 2i to the 7th power. Now notice this is in standard form, not trig form. If you're going to do it in standard form, think about what that would be. That would be 2 minus 2i times 2 minus 2i times 2 minus 2i times, oh my goodness. This is ridiculous. I think one more will be it. Let's see. 1, 2, 3, 4, 5, 6, 7. So if we're going to do this in standard form, we would have to FOIL these two out. We could FOIL these, we could FOIL these. We get some a plus bi here, some a plus bi, some a plus bi. At least it'd be the same on all of them. Let's not forget that guy. But then we'd have to do it again, multiply those two. This would be a nightmare, wouldn't it? But thank goodness we have trig form. This is one of the reasons we've got it. I'm just going to go ahead and get rid of all this. Who wants to do all that? Yuck. All right, we're going to go ahead and do this in trig form. We'll watch it. All right, first we got to change it to trig form. But if you think about it, we're going 2 units on the real and -2 on the imaginary. This is going to form a 45, 45, 90 triangle. Let's just draw it out real quick. So 2 on the real, -2 on the imaginary. Then that means the hypotenuse is going to be 2√2, and that's our r. So we know that this thing is going to be, the r is 2√2, and the theta, I'll go ahead and do this. We can think of the theta in degrees as 315 degrees, or we could do it as 7 pi over 4. Let's just practice radians. Let's not get out of the habit of that. So I'm going to use radians for this. So, excuse me, 2√2 cis 7 pi over 4 to the 7th power. That's what we're dealing with. It's not a big deal. So we know that we're going to do 2√2 to the 7th cis 7 pi over 4 times 7. And, well, let's see. 2√2 to the 7th power. That's going to be the same as 2 to the 7th times √2 to the 7th. And then over here, for the angle, we're just going to have 49 pi over 4. 2 to the 7th power, if you work it out, is 128. If you work out √2 to the 7th power, you're going to have 8√2. 49 pi over 4 is bigger than 2 pi. So we have to keep subtracting off. I'm going to think about that over here. We've got 49 pi over 4. We're going to subtract 2 pi, which is going to give us 41 pi over 4. But then subtract 8 pi over 4 again, and you're going to get 33. Whoops. Pi over 4. And you could keep doing this, but you might see the shortcut. The shortcut is, since I keep subtracting multiples of 8, I'm subtracting 8 from 49, subtract 8 again, I'm going to subtract 8 again. The 4 is just staying the same on the bottom, so we're not changing the denominator. All the actions happening on the top. So 49 minus 8, subtract 8 again, subtract 8 again. Just divide this by 8. What's your remainder? So after you subtract it, your remainder is going to be 1. You're going to have 1 pi over 4 left. So that's what I'm going to put over here. And then when you multiply 8, let's see here, it's going to be 1024 √2 cis pi over 4. And then if we want to change this back, this is not hard at all to do. If we want to change this back to standard form, again, you could just go ahead and multiply it out. Actually, let me show you just to remind you. You could do it the long way. It may not be the long way, but anyway, you could do 1024 √2, and then this is cosine pi over 4 plus I sine pi over 4. And then you could evaluate the cosine of pi over 4, which is √2 over 2, multiply that by this, that gets you your A. Find the sine of pi over 4, multiply it by r, that gets you your b. You could do that, but again, if you know your triangles really well, it's actually probably faster to do the triangles. It's going to take me a while to show you, but if you're like just doing this on your own, it's actually really fast when you know your special triangles. This is pi over 4, that's 45 degrees, so it's going to be our special right triangles again. r is 1024 root 2, which means these sides are 1024. And so, if we put it back in standard form, since that's how our original was given, it is 1024 plus 1024i. And you're done. It took a little bit of work because we had to convert first to trig form. Then we could work with it there. And then we had to convert it back to standard. But think about what I was originally going to do, where I was going to take 7 of these and multiply them out. So much better this way. And what if it was to the 47th power or something like that? So much better this way. So that is powers of complex numbers in trig form in a 17-minute nutshell. All right, see you guys. Bye.